Good afternoon to all of y'all. In the previous video, that is video number 15, we saw what was electric flux. Electric flux is a measure of the number of lines of force emanating from a charge. We saw that the flux d phi through an infinitesimal area dA is given by E dot dA. The total flux is got by integrating d phi. Yes, that is integral E dot dA. We took an example where there was a point charge and we showed that the total flux from a point charge Q is Q by epsilon naught. We did not use the Gauss's theorem or the Gauss's law, yes, as it is called. We did not, without using the Gauss's theorem, we proved that the total flux from a point charge Q is equal to Q by epsilon naught. You can refer the previous video, that's video number 15, for the treatment that we did. Now, if there is a charge Q and if the total flux is Q by epsilon naught, if the total flux is Q by epsilon naught, this flux will be passing through some area. Now that area in this particular case has to be a closed one. Yes, it has to be a closed area. Why should it be a closed area? Because we should not miss out. We are saying it's the total flux. So when you talk about the total flux, you have to encompass the charge fully from all sides. Now, this closed area, let us say, is a sphere. This closed area is, let us say, a sphere. And let us say the center of the sphere, on the center of the sphere lies the charge Q. So now, let us try to calculate the flux through the closed area. The answer we expect is Q by epsilon naught. Yes? So let us see. The flux phi is integral E dot dA. Now you have got a sphere here, and at this point I will choose the area dA. At this point, the electric field E, there is a charge Q here, and if I drew this would be E and dA are in the same direction. And in fact, the two vectors are coinciding with each other. This is dA. In the diagram I am showing it separately, but they are actually coinciding. So, and E would be, if this distance is r, the radius of the sphere is r, E would be 1 by 4 pi epsilon naught Q by r squared. That would be the magnitude of E. The magnitude of E would be 1 by 4 pi epsilon naught Q by r squared. That is the field due to a point charge at a distance r. So, what is d phi now? D phi, which is E dot dA, would be magnitude of E into magnitude of A into cosine of 0 degrees, because E and A are collinear. So this would be Q by 4 pi epsilon naught r squared into dA into 1. That is d phi. So if you integrate to find the total flux, you would have integral Q 4 pi epsilon naught r squared into dA. That would be equal to Q by 4 pi epsilon naught r squared is a constant, comes out, and you have integral dA. Integral dA is nothing but the total surface area of the sphere. So this would be Q by 4 pi epsilon naught r squared into 4 pi r squared. 4 pi r squared in the numerator and denominator cancels, and we arrive at the same result, Q by epsilon naught, in a very simple way. So that brings us to the Gauss's theorem. Now before we go to the Gauss's theorem, we had placed this let us see, we had placed the charge Q at the center. The question we ask now is it necessary to place it at the center? The answer is no. Whether you place it at the center or off center, the lines of force is going to pass through the sphere. All the lines of force will pass through the sphere. Yes? So it wouldn't matter whether you placed it at the center or off center. Will the radius of the sphere matter? That is also nowhere figuring in the final answer. Q by epsilon naught, the flux. So the radius also doesn't matter. Would it matter that if it were not a sphere, but let's say it were a cube and the charge were placed inside a cube, or let's say it was a cone and you placed it inside a cone? In all these cases, whatever lines of force are emanating, they will all cut the closed surface and the answer will still be Q by epsilon 0. So, we now come to the Gauss theorem. The Gauss theorem or Gauss law is that the net outward flux through any closed area enclosing a volume, equals the net charge enclosed in the volume equals the net charge enclosed in the volume divided by epsilon naught. Epsilon naught is the permittivity of free space enclosed within the closed volume, and net charge enclosed within the closed volume divided by epsilon naught, the permittivity of free space. So now we are talking about the net charge. Why are we talking about net charge? We know for a charge Q, the flux is Q by epsilon naught. So for a charge, the flux due to Q1 would be Q1 by epsilon naught. Flux due to Q2 would be Q2 by epsilon naught. So if within this closed area enclosing a volume, if there are several charges Q1, Q2, Q3, etc., then the Gauss theorem simply says that the flux through the closed volume. Now we do a slight change in the way we represent the integral. We put a small circle on the integral to indicate that it is a closed area. Remember, flux can be found out for any area. The area need not be closed. But when it comes to Gauss theorem and you are finding the flux, the area has to be necessarily closed because we are talking about the charge enclosed. So if the area is open, there will be some ambiguity about which charge is inside and which charge is outside. So therefore, it is for a closed volume. That's why I put this circle here. This is equal to Q net by epsilon 0, where Q net would be Q1 plus Q2 plus Q3. And we are saying it is a net outward flux. That means if Q net is positive, there would be an outward flux. If Q net is inward, if Q net is negative, the net flux would be inward. That means if we have a dipole is two equal and opposite charges separated by a distance. So we saw if I have plus Q and minus Q, the lines of force are like this. We saw this in the previous video. All these lines are like that. They leave there, come here. They leave there, enter here. Now if you had let us say a closed volume, we find that whatever exits, that enters. Whatever exits, enters. Whatever exits, enters. So the flux phi is 0. Why is that? The net charge is plus q and minus q. So this would be 0. Yes. Now we shall take a question. Let's say there is a non-uniform electric field. An application of this Gauss theorem we would like to do. There is a non-uniform electric field E given by E is equal to 4xi plus 3yj Newton per Coulomb, where x and y are the coordinates in the coordinate system, coordinates of any point in the xy system. So let us say this is x, y, and I draw the z axis, and let's say we consider a cube here. Let's say I consider a cube here. Let's say this is a cube, and this cube is having a side of let's say 2 meters, and there is a electric field given by this. It is a function of x and y, and we would like to find out rather, what is the charge enclosed? How much is the net charge? How much is the net charge enclosed within this cube? So we shall apply the Gauss theorem, which says that the flux phi is equal to closed integral E dot dA is equal to Q enclosed by epsilon naught. Q enclosed by epsilon naught. So we will find E dot dA. Yes, let us find E dot dA. To find E dot dA, let us list out. The cube has got 6 faces. Let us list the faces. This is face. Which face it is? First we will take the left face. If you take the left face, what is the area vector? The area vector is of the side of the face is 4 meters squared. So this will be 4 into this area vector will point in the minus I direction. So 4 into minus I. 4 into 4 minus I. I can. You take the right hand side face. The right hand side face will be 4 into plus I. The top face would be 4 into plus j, because the area vector points in the y direction. The bottom face would be 4 into minus j. The front face would be 4 into plus k, because along the z axis. And the back face would be 4 into minus k. Now let us write how much is E. If you write E for this face, for the left face, the x coordinate is 0. So if you put x equal to 0, this will vanish, but the y coordinate keeps changing. So it will be 0 plus 3yj. That is the electric field. Yes, 0 plus 3yj. Y keeps changing from point to point. Therefore, we will retain that y as it is. For the right hand face, x is 2. The x coordinate is 2. So 2 4s are, this will be 8i plus, the y coordinate will keep changing here also. So it will be 8i plus 3yj. The top face. the top face, the y coordinate is fixed, it is 2, and the x coordinate keeps changing. So we will keep it as 4xi plus y is 2 for the top face, so it will be plus 6j. For the bottom, again, y is 0 because it's on the xz plane, so 3y would be 0. I will keep changing, so it will be 4xi plus 0. This is a Newton per Coulomb. For the front face, you take the front face, both x and y will vary. So for the front face, we will write it as 4xi plus 3yj. For the face behind, again it will be 4xi plus 3yj. Now let us find E dot A. Yes, let us find E dot A. If you find out E dot A, what you are going to find is that this is vector I and this is vector j. I dot j will be 0. So this is going to be 0. Here you will have I dot I as 1. Yes. And I dot j is 0. So you will get 32 here. Here you will have j dot j is 1 and j dot I is 0. So you will have 4 6 are 24. Here again j dot I is 0 and k dot I is 0, k dot j is also 0, k dot I is 0, k dot. This is 0. So therefore, we have basically the total flux as 4 8s are 32 and 4 6s are 24. So that is going to be 56. That is E dot A. So the total flux phi is 56 Newton per Coulomb per meter square. So you would have the charge enclosed would be 56 by epsilon naught Coulomb. That would be the answer. Yeah. Now let's take up another question. Supposing you had a hemispherical bowl. I am drawing an hemispherical bowl, and there is a uniform electric field E. So uniform electric field E, this field makes an angle theta with the horizontal. Let us say this is a uniform field E. We would like to know what is the flux through the curved surface area of the hemisphere. Now to do this, if you started applying the Gauss law to this surface, it would be very complicated. But we can do a very interesting thing. Suppose you close this hemisphere, and since there is no charge enclosed within the hemisphere, the net flux has to be 0. So whatever flux enters, that much must exit, and everything is entering through the flat surface and exiting through the curved surface. So therefore, all you need to do is find out the flux through this area A. The radius of the shell is given r. So the area vector is pi r squared. Area of a circle, pi r squared. That disk is a circle. Yes, pi r squared. So what is the angle now? This is E, this is A. We want the angle between the two. This is theta, this is 90. This angle is exterior angle, it would be 90 plus theta. So the E dot A would be E into pi r squared into cosine of 90 minus theta. Cosine of 90 minus theta is 90 plus theta, sorry, 90 plus theta. So cosine of 90 plus theta is minus sine theta. So you will get minus E pi r squared sine theta. The minus sign shows that the flux is inward. You take this closed volume, it is inward. So the flux coming out of the hemispherical portion would be plus E pi r squared into sine theta. That would be the answer. Flux through the hemispherical with the, we just change the sign because the net flux is 0. Okay. Similarly, we could take a cone. Supposing there is a cone. Let's say I take a cone here. This is an open cone, and there is a uniform field. Again, we are showing here like that, and this makes an angle theta with uniform field. So parallel equidistant lines of force. Uniform field means parallel equidistant lines of force. So this is E. We would like to find out the flux through the curved surface area of the cone. Now, unlike this case of a hemisphere, the entire whatever was passing through the flat surface was passing through the curved surface. Here you find some of them enter the curved surface and leave the curved surface. So what we shall do is, I shall draw a line parallel at this point like that and cut the cone. So this frustum of the cone, you see whatever is entering is leaving, and whatever is entering the flat surface, that is we close it with a flat surface, whatever is entering the flat surface is leaving the curved surface. So again here, to find the flux through the curved surface of the cone, we only have to find out how much is the flux through the flat surface. So if the radius of the cone is base of the cone is r, so we would have basically the area vector like that, which is pi r squared, and E would be like that. So the angle, this is 90, this is theta, exterior angle is equal to 90 plus theta. Same as here, exterior angle is equal to sum of the interior opposite angles, theta plus 90. Same thing here, exterior angle 90 plus theta. So the flux would be again E dot A, which is E into pi r squared into cos of 90 minus theta. So that will give the same result, E minus pi r squared sine theta. That is, the flux is entering the flat surface. So what is leaving the curved surface would be opposite of this. Since the net flux is 0, there is no charge enclosed within the cone, net flux is 0. Therefore the answer would be again E pi r squared sine theta. Thank you.